I'm going to report on an experiment that's built up under support from the Simons and Templeton foundations here called ALPHA, which is taking the axion experiment, the axion haloscope experiment, in a very new direction. Thank you, Ben, and thank you, Lyman, for excellent talks, which have already done a great deal of introduction to the axion, its production mechanisms. I show here Ben Safdie's, his group's adaptive mesh refinement simulations on the axion production for the post-inflation axion. And as Ben mentioned, in principle, very challenging, we may be at a point, getting to a point where we can predict with confidence the axion mass. Now, this graphic here may lead you to believe that we're home and dry, but in fact, even the placement of that little bar and the width of it, don't be deceived, it represents still an enormous challenge ahead of us. This was a paper that kicked it all off. I looked the other day, I think there's about 3,400 citations. Pierre taught us how to look for dark matter axions, non-relativistic very light axions in our galactic halo. It is basically a very sophisticated radio receiver where one has a high-quality factor microwave cavity inside a very strong magnetic field, and then state-of-the-art preamplifier there to look for a very weak signal on the order of a yoctowatt, quasi-monochromatic, narrow to about 1 part in a million at above background. And then, since one doesn't know the mass of the axion, one needs to tune this in very fine steps, a very small fraction of the Lorentzian bandwidth, each integration period being 10 minutes or an hour or so. So it's a very daunting task, given the many, many orders of magnitude we're in principle looking for. Just show you, all haloscopes have these basic 4 components: a very strong magnetic field, a dilution refrigerator to cool everything down to near absolute zero, the state-of-the-art quantum amplifiers, and a quality factor microwave cavity like this. And this is, I take Haystack, the significance of which I want to point out, because it was the Wright Laboratory and Haystack which I think formed a good basis for a place to develop this new modality for looking at axions, which is a plasmonic haloscope to look in this higher frequency range. And we'll point out the significance of that later on. Haystack was formed as both a pathfinder to go up another decade in mass to take a look at data an order of magnitude higher than where ADMX was trolling, and also as a technology testbed to push on 2 frontiers. One is the noise frontier, and one is the microwave cavity to address the microwave cavity challenges. I think it's well known, and we'll talk about this in a little more detail. I think Haystack is most well known for being the first such experiment to beat the standard quantum limit with a quantum enhancement scheme using squeeze states of vacuum. But in parallel with that, there has been a long-running R&D program in photonics to defeat some of the problems of what happens when you try to push microwave cavities to higher frequency. And this in particular is a problem we think that we've now recently beaten, which is when you now start looking for a transverse magnetic mode to which the axion couples in a microwave cavity. As you go to higher frequencies, you are overwhelmed by a whole forest of TE modes. And we have migrated in a technology known in the microwave source and accelerator community and the optical photonics community known as photonic bandgap structures, which allow us to mow down completely the TE forest, leaving only TEM modes. And then one can actually watch the transverse magnetic modes troll unimpeded without mode confusion, hybridization, and so forth. This is this was mentioned briefly by Lyman here. The name of the game, of course, is signal to noise. These are the terms that we have no knowledge or control over in terms of the axion, the density, the mass, the coupling. These are things that one can improve. One can aspire to build as large and strong a magnet as possible, but there are limitations there. Ultimately, the name of the game in this business for advanced haloscopes is aggressive noise reduction. Here is the system noise temperature. Here's the black body component and the amplifier contribution. Due to a half a quantum vacuum noise here, and for linear amplifiers, an irreducible theorem of quantum mechanics, another half quantum here, you have the standard quantum limit, which we were stuck with up until half a dozen years ago or so in terms of what you could do. And of course, this is, as Lyman pointed out as well, the scan rate figure of merit here for a given coupling constant goes like these quantities here, but 1 over the system noise temperature. Just a quick review, lightning review, of the history of the amplifiers. Original Florida, Rochester, Brookhaven, Fermi Lab used transistor-based amplifiers that were really stuck at several Kelvin, up to maybe 20 Kelvin noise temperature, or about 100 times the standard quantum limit. John Clark at Berkeley, for the ADMX collaboration, made a very big breakthrough in a new way of coupling squids that turned them into gigahertz amplifiers that now really began to approach the standard quantum limit. Conrad Leonard's work then at Colorado for Haystack in making flux pumped, in the invention of flux pumped JPAs. And then more recently, of course, was the advent of squeeze states, where one basically defeats the quantum measurement noise by squeezing the injected noise in one quadrature, but amplifying the signal in the other, which allows one to accelerate the experiment by a factor of 2. And just when you think you could not be more amazed by the quantum magicians, Conrad, now at Yale, after working for several years, he and his group are ready to deploy a system which involves the cavity entanglement and state exchange between the conversion cavity, the cavity on a chip, and to reduce the noise sufficiently that gives us factors of 10 speed up. Now, that's the one frontier which is now well in hand. Pushing the mass up of a haloscope is very difficult business because, you look at where the AMR calculations go, you're now looking at wavelengths which are no longer the size of standard sort of coffee pots, but now are on the order of millimeter to centimeter range, where it's very inconvenient. And of course, scaling the size of a traditional microwave cavity would take a beating like 1 over the, by going down 1 over the frequency cubed in terms of conversion power. The solution to this, or potential solution to this, was published by a group in Stockholm about 6 years ago. It's actually a group that Frank Wilczek, who has also an appointment there at Stockholm, worked with, which was the idea was to break the connection between size of a resonator and its frequency by going to a wire array metamaterial. Metamaterials having a plasma frequency is a property of the bulk, or basically the unit cell, and not the size. So one could, in principle, have a resonator that was both arbitrarily high in frequency and arbitrarily large in volume. And they hearkened back to work of Sir John Pendry, Pavel Belov, and others, who developed very exquisite models of wire array metamaterials, but were not very well tested. And then one day, Wilczek called up and said, look, we want to take this thing seriously. We need a group that can actually do the R&D. Would you take on the prototyping and validating of these, of of the theory here, actually showing you that here, for example, that spacing wires of 50 micron diameter wires, 5 millimeters, would actually give you a plasma frequency of about 10 gigahertz. So we had a large group of people that, in a very organized way, studied this, published a white paper on the possibility of this, and we then launched out our group and started doing some of the fundamental demonstration of wire array metamaterials by what are called S2N measurements, basically transmission measurements, where we made many identical planes of wires spaced by about 6 millimeters. There was one of my undergraduates now at MIT, and then stacking them 1, 2, 3, 4. And then this was, I think, the moment when I became a believer in this, when you actually see that when you start stacking as many as 3 or 4 planes, you all of a sudden have a plasmonic behavior, well-defined plasma frequency. And so we started a large campaign, it's gone on for several years, of looking at the detailed metamaterial properties of these wire array metamaterials. And we were astonished to find, actually we put the theory curve on about 6 months after we took the data, that the agreement in these now semi-analytical theories of the plasma frequency agreed with the data at the 0.1% level. We were, I think, quite astonished by this, and by changing how we interdigitated the planes, transverse and longitudinally offset, even an odd number of planes, we were able to actually look at the absolute agreement with the modeling. So we all of a sudden realized that the models were a pretty good basis for beginning to design an experiment or design some prototypes. Since as you start loading microwave cavities with rods and wires, the surface to volume ratio is going to become very unfavorable, and the Q will drop ordinary copper. We've also begun a large program of looking at superconducting wires and beginning to test them in high magnetic fields. Here we've actually made a miniature waveguide in an X-band waveguide. We've made a miniature wire array metamaterial, and we've tested both niobium and magnesium diboride, which actually looks very, very favorable, very promising as a material we want to use. And this fall, we're now actually going to be testing these things up to 10 Tesla to ensure that their behavior does not fall off with magnetic field. I think magnesium diboride looks particularly promising in this regard. So here, we're now moved into making prototypes of not too different a size that will be the actual alpha. This is a prototype being made by the group at Stockholm, Junu Zhang, and it's a multi-arm spiral design, which looks like it has an extremely good form factor in Q. Actually, didn't have a movie here, but there is in fact a movie of this thing rotating. Here's some of our work at Berkeley. This is a similar type design based on very thin sort of 1.5 millimeter radius copper tubes. There's a little movie of it. It's a bit of a sluggish movie. There's the mode map and the frequency range and form factor. So these look like very promising designs that, and we're here at the collaboration meeting right after this meeting to look at a protocol for how we will make a decision on the design to move ahead for the actual resonator in alpha. There is this site at Yale. Things are building up. They've had the dilution refrigerator for a number of months. They've exercised it. It's all looking very, very good. Here is the site. On the day we had our kickoff meeting, we had both Greg and Amir, when he was there with Templeton, looking down at this thing that kind of looks like a sarcophagus, but this is where, in fact, the pit where the magnet will be. So things are actually coming together in a very nice way there. Here's our projected sensitivity, both for phase 1 at normal conducting, and then phase 1 at Yale, assuming we can make magnesium diboride work. We have a upgrade path at Oak Ridge. Due to the shutdown of the Berlin neutron facility, the Oak Ridge now has a enormous magnet there at the spallation neutron source, 1.7 meters long, 50 centimeter clear bore, and 13 Tesla magnet. And I think this is, if this is a tabletop experiment, we're going to need to strengthen the table. That's a 50-ton magnet there. But if we are forced to go above the 10 gigahertz range to 20 to 50 gigahertz, now we're really going to be in the world of wires where we really have to make the superconducting wire technology work. But this is what the range that we could propose to meet if, in fact, our fears are that ultimately the domain wall decay dominates axions, and we may be forced to look up to 300 micro EV, which would be about 75 gigahertz. We're really fully into the world of a very dense arrays of superconducting wires. Last thing here is a bit of a teaser. I think we're all amazed at these images seen by this worldwide collaboration, the Event Horizon telescope, where an array of 9 telescopes time-stamped and correlated their data to give the extraordinary resolution required to see now there are multiple cases of imaging of black holes. Josh Foster published a paper some years ago which showed that if you have 2 of these devices, haloscopes, depending on what the mass is, but if they were, for example, in a range similar to haystack, the optimum distance would be the several coherence lengths of the axion field would be perhaps something on the order of magnitude of 10 meters. You could see an interference term between the 2 platforms over a period of 12 hours just due to the velocities, the rotation of the Earth's velocity, which changes the, is this 5 minutes or 0 minutes? Oh, okay. So I will, with that, thank the Simons Foundation and also point out the fact that your generosity has also leveraged a great deal of other resources which have helped this project come to fruition. And of course, a lot of preceding work supported by the NSF and DOE. So thank you very much.
Thank you, Karl.